All right. Thank you for the introduction, and also I apologize for arriving late. But with that said, I'll start my presentation. So again, my name is Fredy Ramirez, and today I will be presenting on resiliency of fluctuating layered ordered states in a reduced model. So here's an outline of my presentation today. First, I'll discuss background motivation for the study. Then I'll present the fixed cellular array problem, and then I'll discuss the relaxation of the fixed cellular array problem via the fluctuating vortex array. And then I'll present a summary of results of passive scalar dynamics on the fluctuating vortex array. And finally, I'll discuss ongoing work on active scalar dynamics. So a current subject in magnetic fusion is the E cross B staircase, which motivates our work. So here, pressure profiles in both simulations and experiments have shown coexisting flat spots of high transport and nearly vertical layers acting as mini barriers. In plasmas, avalanches happen in flat spots, and sheared layers due to sonoflows occur in the areas of mini barriers. Some suggested ideas put forth to explain the staircase phenomena are the E cross B shear feedback predator-prey model, where zonoflows are the predator and turbulence intensity are the prey. Oh, sorry, apologize for that. The other is the JAMS model, which is similar to traffic flow theory, where here time delay is due between temperature modulation and local heat flux, which results in a staircase. Yet some questions remain unanswered on such as how does staircase beat homogenization? Is the staircase a metastable state? What is the minimum set of scales to recover layering? But here, so the question remains whether is there a simpler physical mechanism that can produce layering? And the answer to this question is yes. Layering can be produced by simply using a pattern of cells. So now I want to discuss the fixed cellular array problem, which is another way to get a staircase. So for the fixed cellular array problem, let's consider a cellular lattice of marginally overlapping stationary cells. There are two questions that come up. What is the transport like? And what does the profile look like? First, there are two time scales, the rotation rate of the cell, and then the diffusion rate across the boundary of the cell. The ratio of these two time scales is the Peclet number, which for layering to occur must be much, much greater than 1. So what this means is that there's a faster rotation in the cell, and there's a slow diffusion timescale across the boundary of the cell. Due to these two timescales, there's a global transport described by an effective diffusivity, which is proportional to the background diffusion times the square root of the Peclet number. And the important thing to mention here is that this effective diffusivity is not a simple addition of process such as background diffusivity plus the diffusivity across the cell, but instead it's a geometric mean. And so for the profile, let's consider, for example, a concentration of dye injected through the right boundary here, or left boundary. And so as the dye travels through the array, it gets trapped within cells, and over time, slowly, some dye diffuses over to the other cell through the cell boundary and falls into the other cells and gets trapped there. And so therefore, this results in the following figure by Rosenbluth back in 1987, which shows the steep transitions in the density exist between each cell. And so again, this is a perfect example of layering, and it is simply due to two consequence of two time scales, the rotation of the cell and the diffusion across the boundary of the cell. And so the important thing here is that the staircase arises in a stationary array of passive eddies. And note that there's no feedback involved in this process. The global transport hybrid is the fast rotation in cell and slow diffusion in the boundary layer. But figures such as this, or a setup such as this, may be argued that it's contrived, it's not self-organized, that the cellular array is severely constrained. So my work now is on the dynamics of a less constrained cellular array, or in other words, vortex array with fluctuations. So now I'll be discussing the relaxing the fixed cellular array via the fluctuating vortex array. So we want to study, again, a much more general and less constrained version of the cellular array. So here now, the cellular array will have fluctuations and will jitter. And the question we want to answer is, how resilient is the staircase in the presence of these small variations to the fixed vortex array? And in the process of studying the resiliency of the staircase, we aim to answer the following. What happens to interspersed regions of strong scalar concentration mixing as cells relax? What about general cell interactions / behaviors? What is the behavior of the scalar trajectory through the vortex array? How does the increase of scattering in the vortex array affect transport and scalar concentration? And so to answer these questions, we use the idea of a melting vortex crystal. So again, just to remind the audience why we're doing this, we know that a system with two disparate timescales forms a staircase. Now we want to consider fluctuations and see whether the staircase will survive. The vortex array is an alternative way to view convection cells. So here I present the two-dimensional Navier-Stokes equation, which is written in non-dimensional form. And so again, this is just basically the vorticity equation. We have our forcing function, and then we have our drag. And so here, the vortex array is simply the array of cells again, and fluctuations is related to turbulence-induced variability in the structure. The fluctuating vortex array allows us to study a less constrained version of the array, and so this is an improved model of cells near marginality. Here, the fluctuating flow is created by slowly increasing the Reynolds number, which is we denote as capital omega here in the Navier-Stokes equation. And so by increasing the Reynolds number, this modifies the forcing and drag term. Both have within these terms, they have the capital omega term. And so by increasing the Reynolds number, this scatters the vortex array. And so from here, we see whether how resilient is the staircase when we increase the sorter in the vortex crystal. And so from our vorticity equation here, we output the spring function at different evolutionary stages of the fluctuating vortex array, and we insert this into a passive scalar transport equation to study the resiliency of the staircase structure. So before I show results here, I just want to provide a quick comparison of the vortex array model to drift wave turbulence in fusion devices. So we have the vortex field here, and then we have drift wave turbulence. And so we have inhomogeneity in the vortex field is the scalar concentration gradient. In drift wave turbulence, we have a gradient in the density, gradient in temperature. For Reynolds numbers, we work with from Reynolds numbers from 0 to 40, which are similar to effective Reynolds numbers found in drift wave turbulence, which range from 10 to 100. Here, dissipation is due to Landau damping. And then we have flux, which for us is the scalar concentration. Drift wave turbulence is heat flux, or also the turbulence intensity. And Sono flows, we have for Sono flows, we can think of them as the boundary layer between cells. And for drift wave turbulence, we have E cross B shear flow, which is in the poloidal direction. So now we want to see what happens to the staircase. And so first, again, I just show quickly here. So we have a vorticity equation, and we output the stream function and insert this into the flow velocity term in the passive scalar transport equation. And so here we apply fixed flux boundary conditions in X, and then periodic boundary conditions in Y, and then you let the basically let the passive scalar evolve within this flow. And so to begin with this, we start off with a weakly fluctuating vortex array in order to touch base with the fixed cellular array that we studied earlier. And so here's an example of a baseline staircase structure. So here you can see that this is basically essentially the weakly or the fixed cellular array. And so we average, so we take an average of y prime and plot a function of x prime in two different orientations in order to see the staircase structure, as you can see here. And so this is for this case is the baseline staircase. And we can see here that this is for omega equals 5.5. So anything below this value of 5.5 results in this same staircase structure, since the flow is frozen into the forcing function, which provides the vortex array. So now that we have our baseline staircase structure, we want to increase fluctuations in the flow and see whether the staircase structure survives. So we find in our studies that the staircase is resilient to fluctuations. As you can see here, we see a lot of different staircases. And so we indicate here steps are regions where there's basically the change of the average of scalar concentration over y prime over the change in x prime is approximately equal to 0. And is clearly distinct from jumps, as you can see here. And so as we increase fluctuations in the vortex array through Reynolds number, we can see mergers connections in the vortex structures. And so these vortex mergers are shown in the scalar profile plot as mergers in steps. And so as we increase jittering, staircase steps merge together. And also you can see here, here I also indicate the step size, delta x. So for example, the baseline staircase structure, we have delta x equals 0.65. And as we increase the Reynolds number, we begin to see that the step size also increase from what I showed earlier. And so again, the main point here is that despite the vortex array becoming more turbulent, the staircase structure does not collapse. Staircase steps become less regular by simply merging into longer steps. So that's great. We show that staircases are resilient to fluctuations, but how do we quantify this? So to quantify this, we establish a set of criteria to give precise meaning to the statement of resiliency. The first criteria is that Peclet must be much greater than 1, which, as I discussed earlier, is a necessary condition for the formation of transport barriers in the process of scalar mixing. Again, you want to have fast rotation within the cell and then slow diffusion across the cell boundary. And so for our simulations that we ran, we found that Peclet much greater than 1 criterion is satisfied for the range of 0 to 40 for Reynolds numbers. As you can see here, it kind of plateaus for values of omega equals 35, around 17.5, which is still good enough. And as you can see, I showed earlier, we have still a staircase structure present in the simulation. A second criteria is that a staircase should maintain a sufficiently high curvature, which is equivalent to sustaining a sufficient number of steps. And so here we have the curvature plot. And for our studies, we show, or our studies suggest that kappa greater than or equal to 1.5 is an adequate value for the staircase. So with that said, now I want to discuss transport in the fluctuating vortex array. So first I want to discuss that before the staircase structure forms, the scalar concentration flows quickly in regions of strong shear and around vortices, as you can see in this figure here. So essentially what happens is that the staircase barrier forms first, and as the scalar travels along cell boundaries. And over time, the vortex entrains scalar by a kind of homogenization process via the synergy of differential rotation and diffusion. And in addition to this, we also quantify the scalar concentration front speed as it travels across the vortex array. So here you just have a little drawing for as an example of the frozen vortex array and then the fluctuating vortex array. And we find that as the vortices scatter, this leads to an overall decrease in scalar concentration velocity, which agrees with the least time criterion and a similar idea to that of light, or the scattered path of light in the atmosphere. Next, we also investigate how the effective diffusivity changes in the fluctuating vortex array. So as cells fluctuate, the effective diffusivity deviates, but remains close to the fixed cellular array effective diffusivity, which I denote as DRB, as you can see here. So we have the D star divided by the fixed cellular array effective diffusivity. And what we find, or the important thing to note here, is that dimensions and the turnover velocity of the cells affect the transport. So this what we observe from this plot here is that this suggests that the fixed cellular array effective diffusivity is a good approximation, even if cells are irregular, since effective diffusivity deviates but remains close to that of DRB. And what we find is that as long as the boundaries of the cells are maintained, the effective diffusivity and transport does not change significantly. In this for this project, we examine the effects of cell dimensions, dx and dy. So dx is the length of the cell along the mean gradient, and dy is the length of the cell perpendicular to the mean gradient. And since our emphasis is more on the impact of cell geometry on pattern formation. And so here we can see that there's a similar or a correlation between beta, which is again dx over dy, and d star over drb. And to show this a little more clearly, here I provide another effect. So the effective diffusivity at different orientations. So we have negative pi over 4 and pi over 4. So this corresponds, so this blue and red point corresponds to this flow structure here. And the blue point corresponds to this figure here. So we do a scan, basically, we study the effective diffusivity within this region in black here. And so what we find again is that effective diffusivity increases and decreases or decreases if the cell length along the gradient dx increases or decreases compared to the length perpendicular to the gradient. And so as you can see here, kind of cells on average remain around beta equals 1, but there are clearly cells that are larger in size due to cell mergers, which cause the deviation of the effective diffusivity. And so here we have this large blue shell or cell, as I boxed in here in red. So we have the dx length is much greater than dy, so this will result in the effective diffusivity deviating above what the fixed cellular array effective diffusivity would be. And so with this, I want to just summarize the work done or work on the passive scalar dynamics. And so what we find is that staircases form and are resilient and persistent to increasing Reynolds number. We also find that scalar concentration travels along regions of strong shear. The important thing here is that the staircase barrier forms first and vortex homogenizes in the scalar at a later time. The scattering of vortices leads to an overall decrease in scalar concentration velocity. And if background diffusion is kept fixed, cell geometric properties can qualitatively approximate the trend of the effective diffusivity, as I showed earlier. The effective diffusivity of the perturbed vortex array does not deviate significantly from that of the fixed cellular array. And quickly, I would just like to mention that this theory presented here can actually be tested with experimental data. So there's currently a work in progress at the LAPD or Large Linear Magnetized Plasma device at UCLA, where a vortex array can be created in the device. So through a modification of a cathode plasma source with the Zener mass, as you can see here, we can form basically a current channels in a cellular pattern, which will lead to a formation of a staircase structure. And so here the staircase can be subject to controllable amount of low frequency density fluctuations, which act as a noise source and will allow us to test hypotheses and models of staircase resiliency, such as those I presented in this presentation. The results of this experiment will yield a unique set of observations that can be used to test the staircase model. And so hopefully it can present more details on this in the future. So now I want to discuss current work on active scalar dynamics. And so now that I discussed passive scalar dynamics, a logical next step to explore is the effects that an active scalar has on the cellular array and inhomogeneous mixing. So we convert the passive to active, and this will result in effects such as flux expulsion, which is the simplest dynamical problem in a non-ideal MHD. And one might ask, why this model? So as magnetic fields get expelled to boundaries, it will hold the cells together, which will lead to a much more rigid staircase. So for our problem, we turn the passive scalar here equation into an active scalar, and this creates basically a feedback between magnetic fields and vortices. And here we have m squared term, which is m is just equal to the alphane velocity over the characteristic flow speed. So what this means is that the strength of the background magnetic field plays an important role. So before I discuss the kinematic and dynamic regime, I want to just first present or consider a linear magnetic potential profile, and as you can see here. And so here, then we have the cells and we have the magnetic fields passing through the cells. And so as the magnetic fields get expelled to the boundaries of the cells, we expect that the vortex array will homogenize the profile in areas of vortices. And we expect that the magnetic field will maintain or restore the cell array structure when fluctuations are present. But now I want to discuss, so one of the important things here is that flux expulsion only occurs in the kinematic regime, and it is also useful to explore the dynamic regime, AKA the vortex bursting regime. And so since the alphane velocity is proportional to the background magnetic field, the strength of the magnetic field will play an important role in the dynamics of the cellular array. So as you can see here, m squared times the magnetic Reynolds number less than 1 results in flux expulsion, and greater than or equal to 1 or of order 1 results in vortex bursting. So again, if keeping magnetic Reynolds number fixed and the characteristic flow speed fixed, if B naught sufficiently small, we get cell strengthening, and if B naught is large, vortices will not be allowed to form. And so through scans of background magnetic field values, we will address what occurs to the expulsion of neighbor cells and their interactions. So now I want to discuss the magnetic staircase. And so in a periodic system, we basically study the process of inhomogeneous mixing by first initializing the active scalar using just a simple cosine term. And so again, for all simulations, we fix the magnetic Reynolds number and only vary values of B naught and capital omega, which is just our Reynolds number. And so as a baseline case, we first study the evolution of the active scalar in the frozen vortex array for a value of omega equals to 1 and sigma equals to 1. So this is just right at the boundary of where like flux expulsion and vortex bursting occurs. And n equal 2 and n equal 4 just correspond to the wave injection number in the forcing function I presented earlier. But what this means is that you essentially, n equals 2, you get like a 2 by 2 cell, and 4, this means you get like a 4 by 4 cell array. And so what we find is again that the active scalar is homogenized within regions of vortices, and so thus producing steps in the profile, as you can see here. The magnetic field lines, so this is a contour of the magnetic field lines. It's expelled at the boundaries and hold the cell together. But magnetic field eventually decays in 2 dimensions, so the structure is only temporary. As you can see at a later time, the magnetic fields dissolve and the whole system just kind of, or the whole structure kind of vanishes. In addition to this, we also find that as the magnetic Prandtl number approaches 1, a variety of layering patterns appear. So we have here for different magnetic Prandtl numbers and different sigma numbers, that we get these different structures, which produce also a staircase structure in each case. And in addition to this, we also, even within the same cases, we find transitions between different layering patterns, as you can see here. So in this case, it transitions over to this case where we still see a layering pattern, but the contour of the active scalar looks different. And so to understand the dynamics of the active scalar in homogeneous mixing, we study the evolution of the following quantities: energy, both kinetic and magnetic, the mean squared magnetic potential, and then the disruption parameter, which just measures the disruption of the vortices, the profile curvature, and energy dissipation rate. So here we start first by presenting the evolution of the energy, as you can see here. So the time trace energy shows an initial suppression stage, followed by a kinematic decay stage. And so during the suppression stage, basically the magnetic field lines hold the structure together. And so here we kind of have more of a constant ratio of magnetic energy to kinetic energy. And in some particular cases, such as these, we even see in between these like transitions, there's a jump in EM or over EK. So here we have 2 different layering structures, and which I'll show later also appears in the mean squared magnetic potential plots or time trace as a change in time scales. So the important thing here is that we have a suppression stage where magnetic field lines hold the system together, we get layering, and then we have a kinematic decay stage where then the system goes into, or magnetic fields decay, and we have a purely hydrodynamic flow. And so here's plots of the evolution of the mean squared potential. And so what we find is that there's at least, again, 3 time scales, which corresponds to our problem. So we have a flux expulsion, which is an initial time scale and occurs very early on. And then once the system gets held together by the magnetic field lines, we get a magnetic diffusion time scale, which holds the array together while there's jittering present. And finally, as the magnetic fields dissipate, we get this viscous time scale. And so here I just want to show that for magnetic Prandtls equal to 50, as I showed earlier, there was a transition in layering. And so what we observed is that this T2 basically, or the second magnetic diffusion or intermediate timescale breaks up. And so within these two time periods here, well, we get different forms of layering. And so by studying, so for the case of magnetic Prandtls equal to 50, sigma 1, this particular case, we also look at, as I mentioned, the disruption parameter, so how the vortices get disrupted, and then also the curvature of the profile. And so here the disruption parameter is just 1 minus the area or the integral area of the Okubo-Wise field over the fixed cellular array Okubo-Wise field. And so 1 means that the vortex has been purely disrupted, and 0 means that that there's no disruption present. And so when we get these two different transitions in layering, as you can see, the first transition, we get this flat region here. And in the second transition, we get another flat region, but the vortex array gets disrupted slightly. And what we find is also that in the curvature plot, a trace of the curvature, we see these smooth kind of transitions within regions of layering. And in addition to this, we see that for dissipation, we find that there's a balance between magnetic and kinetic dissipation once the layered structures form. And whenever there's no layered structure, we get all these like the kinetic dissipation and magnetic dissipation fluctuate a lot more. But eventually, as you can see here, again, the magnetic field dissipates over time and the layer structure dissolves. So we no longer see, or as you can see here in the magnetic field contour, we don't see the magnetic field lines holding the structure together. And so with this, I just want to summarize the work here. So we demonstrate that layering occurs both in flux expulsion and vortex bursting regime, and different patterns appear. And there's also transitions between different forms of layering. There's 3 time scales present and appear in the mean squared magnetic potential time trace. And when layering occurs, there is a balance between the magnetic energy and the kinetic energy, which is also reflected in the dissipation rate. When layering occurs, the profile curvature maintains a kind of constant state. And the important thing to note here is that this is steady state is transient and lasts only for a brief period due to magnetic field decay. So for future work, the next thing is to introduce a stochastic magnetic potential forcing. And the question here would be whether the stochastic forcing will reinforce the layering, or will layering spontaneously reappear if we introduce stochastic magnetic forcing later during the turbulent state, or once the such as delta equals 1, which means that the vortex array has been fully disrupted. And with that, I just want to say thank you and happy to answer any questions.
Thank you, Fredy, for a very interesting talk. So we already have a question.
I want to understand some elementary features. The forcing function F omega that generates your vortex array, that's a sort of given, right? You actually specify F omega is a biperiodic function in X and Y, and that's permanently there. No matter how much you stir the system, there's at the bottom there is this sort of, it's like a one-body potential, right?
Yes, that's correct.
So, that being the case, I would think that no matter how much noise you put on, if you ask for the time average vorticity pattern, there would always be a background spatially periodic structure. Is that correct?
Yes. Yeah.
Okay, I see. Okay. And the difference between what you guys did and what Perlekar and Pandit did is that they didn't have a scalar concentration field in addition. Is that right?
Yeah, that's the thing. Yeah, they didn't have a scalar concentration field within the this like melting vortex crystal. They just studied basically this particular problem.
Of the vortex pattern.
Yeah.
By the fluid.
Yeah.
I see. Okay. All right. Thanks.
There's another question. Go ahead.
Well, I'll have
two questions.
If you were to transiently decrease your, if I understand, Beckley much bigger than 1 corresponds to Cubo very small, right? So if you were, no. Okay, so if you were to transiently increase, well, decrease the Beckley, how fast would it recover?
So your question is whether so if I were to decrease the Peckley number, how fast would I recover layering?
Yes.
Okay. I do not have an answer to that. I did not look at basically the time scales of how layering is developed.
Fredy, I think Pat wants to say a few words.
I mean,
Okay.
you missed the point. Peckley is not a control parameter. The only control parameter is the Reynolds number. Okay, if you go back, Fredy, to the plot of Peckley versus Reynolds number for your resilience thing, there you go. You see, omega is the control parameter here. The forcing is buried in that, or actually for fixed forcing we vary viscosity. So Peckley goes along. Now, of course, you reduce the Reynolds number, and yes, you go back to a nice, beautiful, ordered staircase.
Do you have a follow-up?
I'll ask it directly to Pat.
Oh, good. I think that's wise. So other questions for our speaker? Yep, David.
So the fluctuations in your model are they're dependent on the nature of the instability of the flow you're forcing. Right?
Yeah.
Which is in a way out of your control. I mean, so if maybe you haven't taken other flows, but you could take other cellular flows, for example, with different phases between the rotations, which would then have a very different instability pattern, conceivably, and might give something very different. Maybe that's what you were getting at in your last slide there.
Yes is the answer.
I mean, you've kind of lost control of the fluctuations sometimes.
Yeah, that's correct.
It would be nice to have them under control, I guess.
But we also have to deal with your predecessor from Leeds, right? So we need to pump the magnetic field.
Who's my predecessor from Leeds?
Cowling, right? The B field decays.
Cowling has nothing to say about this problem.
Yes, I mean, that's why you need a stochastic forcing of A here.
Oh,
that will, in other words, the field then will hold the thing together, right?
That is Zeldovich rather than Cowling.
Oh, close enough. They all
Okay.
These guys
I'll take one last question because it's our next speaker asking it.
Yeah, so probably I missed some point, but you mentioned that three time scales. Then you also mentioned that magnetic Prandtl number is 50, more than 1. Then I have thought the resistive scale is much smaller than viscosity scale. Okay? Then I had thought, so magnetic fluctuation always feels the viscous dissipation already. So then I still don't fully understand why you said finally it's in your time scales. First you said flux expulsion and then magnetic resistivity. So I still don't fully understand why viscous dissipation is the final process. That's my question. Highly probably I missed some point.
Okay, yeah. So here, so this is still kind of ongoing work, and the details haven't been really polished out. But so the reason why we say that there's a final viscous timescale is simply due to, again, just the magnetic field dissipates. And so what we get in the end is that there's just a purely hydrodynamic flow, which then we have a longer time scale due to just viscous dissipation in the flow structure. But again, this is still kind of like very early on work. And so hopefully soon the details of these timescales can be polished out, but at least this is like what we kind of see initially.
Okay, let's thank our speaker again. Thank you, Fredy.